Hello everyone, and welcome to this video presentation. My name is James Cho. I'm a graduate student at Georgia Tech, and today I will be giving a research paper presentation for the class Cyber Physical System Security. And the research paper will be RoboADS, Anomaly Detection Against Sensor and Actuator Misbehaviors in Mobile Robots. The assignment was to create a video presentation discussing a cutting-edge cyber physical system security research paper. The specific paper was published and presented at the IEEE International Conference on Dependable Systems and Networks in 2018. Here's the agenda for this video presentation. It generally follows the flow of the research paper. Before we get to the research paper, we're going to cover a few broader definitions in order to better understand the scope of the research. So first, what are cyber physical systems? They are physical and engineering systems whose operations are monitored, coordinated, controlled, and integrated by a computing and communicating core. So robotics. A robot is a device made up of mechanical and electrical components that sense, thinks, and acts. Global spending on robotics will approach $188 billion by 2020. It is only becoming more ingrained in today's society, more prevalent. Robots are deployed in many areas, including defense, security, agriculture, manufacturing, household, and entertainment applications. This research paper focuses specifically on mobile robots. Mobile robots are a great example of cyber physical systems because they combine sensors, actuators, and embedded computing devices in order to operate in both the cyber and physical domains. Like any cyber physical system, mobile robots are vulnerable to attacks. The safety of mobile robots are threatened by cyber and physical attacks, as well as software and hardware failures through cyber and physical channels. And we're going to discuss that more on the next slide. Robot safety can be improved by early detection of problems, and that's what the authors of this propose, or that's why they designed this robot anomaly detection system, was to specifically identify misbehaviors in sensors and actuators so that they can be detected early and future problems can be avoided. Here are some examples of mobile robot misbehaviors. The misbehaviors are the robot acting a way it shouldn't, and the channel is either the attack vector or just the cause of that misbehavior. So a cyber misbehavior through a cyber channel would be a denial of service attack. A physical misbehavior through a cyber channel would be GPS spoofing of a drone. And this is a real-world example of this picture is of a surveillance U.S. military drone that was taken down. Well, one of them was taken down by the Iranian Cyber Warfare Division. It was GPS spoofing of a drone of the drone. So it was a cyber channel that GPS spoofing was, but it changed the physical location of the drone and inevitably or eventually brought it down. A cyber misbehavior through a physical channel would be a processor overheating. The physical channel being the environment. Cyber misbehavior would be the processor itself. And then a physical misbehavior in a physical channel would be something such as a flat tire. The scope of this research is it's focused on detection of misbehaviors that actively influence robot behavior and cause damages in the physical world. As a disclaimer, the scope of this research does not include the Terminator. It was just the most extreme example I could think of a misbehavior that would actively influence robot behavior and cause damage to the physical world. Misbehaviors are deviations from planned mission execution. And, this research is origin agnostic, so the detection system does not try to attempt the cause of a sensor or actuator misbehavior or of both, but rather just if sensors and actuators are misbehaving. The researchers used a model-based estimation approach. Misbehaviors were modeled as data corruptions. The RoboADS system builds correlations between potentially corrupted sensor readings and control commands. The robot states were used as intermediate authentic sensor readings, and control commands were estimated. And then discrepancies between estimated versus measured values were how misbehaviors were indicated. Some major challenges for this research was the non-linearity of robots and their susceptibility to noise, which is very common amongst all robot research, specifically other anomaly detection systems for robots as a major challenge across the board. The disastrous physical consequences of misbehaviors, and specifically when the physical consequences were almost immediate with the misbehavior, that's when it was most challenging for these researchers. If things happen instantaneously, it was very hard for the sensors to detect them. And then also the sensor condition. There's no way to know whether a sensor is healthy or if it's corrupted, and a control group sensor could not be used because any sensor on the robot is susceptible to being corrupted. This is the mobile robot system model. The planner is the control center of the robot. The robot interacts with the physical world through sensors and actuators on its physical layer. Physical signals go through sensing workflows and reach to the planner. And the control units in the planner generate control commands to accomplish given missions. Control commands are executed in the physical world via actuators. This is the mobile robot misbehavior categorization. Misbehaviors could originate from both physical channels and cyber channels. The consequences could be data corruptions in sensor readings and control commands. So the sensing workflow is each sensing procedure, including the capture of physical signals, such as electromagnetic waves or acoustic waves, as well as signal digitation, data processing, and encoding. And the actuator workflow is defined as any procedure that receives, decodes, amplifies, and executes control commands in an actuator. Now we're going to get into robot formal modeling. The first is the kinematic model, which models robot state transitions driven by control commands. The second is the measurement model, which models the relationship between sensor readings and robot states. And a combination of these two creates the dynamic model of a general nonlinear robot. Next is misbehavior modeling. Here are both misbehaviors and their respective vectors. As a reminder, actuator misbehavior directly alters the control commands executed by the actuators in an actuator workflow, and sensor misbehavior tampers data in a sensing workflow and results in wrong sensor readings received by the planner. Using these two equations, mobile robots can be modeled as a dynamic, nonlinear, discrete time system. For the first equation, let X represent a robot state. For each control iteration K, plan control commands U are generated by the planner. Here, the vector zeta represents process noises to account for external environment disturbances. For the second equation, after robot states transition from xk-1 to xk, the planner receives new sensor readings represented by a measurement function h, and xi is a vector of measurement noises to account for sensing inaccuracies. Here's the algorithm for the RoboADS design. There are 4 modules: monitor, multi-mode estimation, mode selector, and decision maker. The first module, monitor, receives a list of control commands from the control unit, and after execution of commands collects sensor reading data from all the sensors. The second module, multi-mode estimation, is the heart of the RoboADS algorithm. It compares estimated and planned control commands to detect actuator misbehaviors. It compares estimated and received sensor readings to detect sensor misbehaviors. It calculates estimates along with hypothesis tests, and uses modes to represent subsets of potentially misbehaving sensors. It runs NUISE, and you see it there, which stands for nonlinear unknown input and state estimation. It runs that algorithm in parallel for each mode, and it uses this to predict the likelihood of each mode, which allows the system to correctly identify clean or corrupted sensors and corruptions in control commands, and model noises as error covariance matrices to minimize variance of estimates and normalize anomaly vector estimate errors for hypothesis tests. The next is mode selector, which compares the likelihood of each mode. It chooses the mode with the highest likelihood to best represent the real world. It then updates state estimations for the next iteration and uses anomaly vector estimates of the selected mode to improve the decision-making process. And finally, there's the decision maker, which conducts a chi-square test to check if estimated sensors and actuator anomaly vectors exceed thresholds. It raises a sensor misbehavior alarm when the number of sensor anomaly positives exceeds acceptable levels. It also raises an actuator misbehavior alarm when actuator anomaly positives exceed acceptable levels. The test results go through sliding windows and detect only alarms when a certain number of positives appear in constructive iterations. Now we're into evaluation. So for testing, the effectiveness of the model was measured in terms of the number of false positives and false negatives generated by the algorithm. The efficiency of the model was evaluated by detection delay, which measures the period between when a misbehavior occurs and when the system correctly captures the event, and some detection performance influences to consider choice of the detection window size, detection criteria, as well as a detection confidence level. These were the robots used in the two tests. On the left, you have the Capera robot, and on the right, you have the Tamiya robot. In the center is the test environment that was used. Here were the attack failure scenarios for both robots. If you take a look, they start as a singular test, and as they progress through the scenarios towards the end, there's combinations. If you look at scenario 11, IPS and wheel encoder logic bomb, it's a combination of scenario 3 and scenario 5. This was generally the trend for most of these scenarios. Here are the results for the Capera robot. It was tested under multiple attack failure scenarios on the previous slide. For the Capera robot, RoboADS was highly effective in identifying sensor and actuator misbehaviors with an average false positive rate of 0.86% and an average false negative rate of 0.97%. Average detection delays for sensors and actuator misbehaviors was 0.35 seconds using a 2 of 2 decision criteria sliding window, and average detection delay of 0.61 seconds using a 3 of 6 decision criteria sliding window. For test 2, the Tamiya RC car, the RoboADS was somewhat less effective in identifying sensor and actuator misbehaviors. The average false positive rate was 2.77%. The average false negative rate was 0.83%, and the average detection delays for sensor misbehaviors and for actuator misbehaviors was 0.33 seconds. Here's a summarization of the test results. You can see the fastest detection delay, or the shortest time, was scenario 6, LiDAR denial of service, and the longest detection delay was wheel jamming, scenario 2, 0.76 seconds. I think it makes sense that a actuator would have the longest delay, specifically something like wheel jamming, because it's hard to determine whether or not a wheel is jammed or is just um, moving slowly. On the right, you see the mode definitions for each one of the detection results. Some limitations of this research, as previously discussed in the challenges, there was a no control group sensor. That is to say, there was no sensor that could be used as a baseline in order to determine whether the other sensors were good or corrupted, and that's because any sensor on the robot could be corrupted. The misbehavior is modeled as aggregate data corruption, which means no root cause insight can be determined. And another limitation is, I guess, a vulnerability within this anomaly detection system is that if a sophisticated attack were to hop attack vectors, it could successfully avoid detection, or at least it would be much more difficult to detect using this system. In closing, misbehavior poses huge safety risk to mobile robots. RoboADS did prove effective for misbehavior detection within a small delay window. However, they only use 2 robots. They need a much larger sample size in order to find statistical significance, but also it's a very challenging field to find statistical significance because of the variance in operations for robots. But the RoboADS system is unique because it handles nonlinear systems and because it can detect both sensor and actuator misbehaviors. For future work, I would recommend that the researchers expand the scope outside of misbehaviors that only cause physical damage and consider cyber damage as well. Another thing that needs to be expounded on is identifying root cause, an anomaly detection system for mobile robots that could first identify misbehaviors in sensors or actuators and then drill down to discover the root cause would be very useful. And then past that, develop response actions to counter misbehaviors once root causes can be determined. Thank you for tuning into this video presentation. It was a pleasure to review this paper. I hope you enjoyed it, and I'd like to thank you for viewing.